Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to have you here because honestly, today we are embarking on a truly fascinating journey. We are going to decode the ultimate biological camera. And yeah, I'm talking about the human eye. I mean, just think about it for a second. From the exact moment you wake up to the second you go to sleep, your eyes are processing just an unimaginable amount of information. They are rendering the world around you in high-definition, three-dimensional color, and they're doing it seamlessly and instantaneously. There's zero lag. But how exactly does this miraculous piece of biological hardware actually work? And, what happens when things start to get a little blurry? Today, we are going completely under the hood. We're going to break down the anatomy, the incredible physics of how our eyes focus, the common defects that affect millions and millions of people, and finally, the stunning secrets hidden within the very light that our eyes capture.
Okay, let's dive right into this. Here is our roadmap for today's visual journey. We'll start with 1. Anatomy of the eye, move to 2. Power of accommodation, 3. Myopia, 4. Hypermetropia, 5. Other defects, and we'll wrap up with 6. Prisms and light.
Section 1. Anatomy of the eye, the biological camera.
So before we can get into vision defects and the physics of light, we really have to understand how a healthy eye functions. Let's trace the exact chronological path that light takes, the absolute millisecond it reaches your face. Step 1 is the cornea. This is the outermost part of the eye. It's curved, kind of like a convex glass lens, and it acts as your eye's primary shield against bacteria and hostile elements like dust. But its main job? It actually handles about 70 to 80% of the light refraction, or bending, before the light even gets deep into your eye. From there, the light passes through step 2, the aqueous humor. Now, this is a water-like liquid sitting right behind the cornea, and its primary job is absolutely crucial. It balances the atmospheric pressure outside your eye with the blood pressure inside your eye, keeping the whole shape perfectly stable. Next up, we hit step 3, the pupil and the iris. The iris controls the size of the pupil, basically regulating exactly how much light gets to enter the deeper eye. If you've ever flashed a light in someone's eyes, you've seen the iris instantly contract the pupil to protect those delicate inner mechanisms. It's totally automatic. Then light hits step 4, the crystalline lens. Unlike a hard glass lens, this biological lens is completely flexible. It does the final, fine-tuned bending of the light to create a real inverted image. And finally, that image is projected onto step 5, the retina. The retina acts exactly like the screen in a movie theater. Once the light hits this screen, electrical impulses are generated and fired straight down the optic nerve to your brain. And your brain is what actually flips the image right side up so you can understand what it is you're seeing.
Now, that biological screen, the retina, is entirely coated in two very distinct types of photosensitive cells, rod cells and cone cells, and they're named quite literally after their physical shapes. Rods are basically your built-in night vision goggles. They are highly sensitive to light intensity. So if you're driving at night, or walking down a dimly lit street, or just trying to navigate your bedroom in the dark without stubbing your toe, you are relying heavily on your rod cells. Fun fact, pigeons actually have very few rod cells, which is exactly why you literally never see a pigeon flying around at night. Humans, on the other hand, have enough to let us function pretty well in dim environments. Cone cells, on the flip side, are the color decoders. You can easily remember this, C for cone and C for color. They require bright light to function properly. And that's exactly why when you're in a super dark room, you can make out shapes using your rods, but everything looks sort of washed out, gray and colorless. Your cone cells simply don't have enough light to turn on and do their job.
Section 2. Power of accommodation, the eye's ultimate autofocus.
Let's move on to what is arguably the eye's most incredible superpower, the power of accommodation. This is the ability of the eye's flexible crystalline lens to actually adjust its own focal length. Think about the physics of a lens for a second. The distance between your eye's lens and your retina, where the image absolutely must land, is fixed. It physically cannot change. However, the distance of the objects you're looking at in the real world is constantly changing, right? One second you're looking at your phone right in front of you, and the next second you're looking at the moon in the sky. Since the object distance changes but the image distance inside your head is fixed, the math dictates that the focal length of the lens itself has to change. If our eye lens were made of solid glass, this would be literally impossible. But our biological lens is flexible. It is controlled by these tiny little things called ciliary muscles. When these muscles contract or relax, they physically squish or stretch the lens. They are changing its thickness and, as a result, altering its focal power in real time. It is the ultimate biological autofocus.
But even superpowers have their limits.
25 centimeters is scientifically recognized as the standard near point for a perfectly healthy human eye. What this means is that if you bring an object, like a book or your phone, closer than 25 centimeters to your face, your eye is going to really struggle to focus on it. You can force it, sure, but doing so puts immense strain on those ciliary muscles. Meanwhile, your eye's far point is theoretically infinity. A healthy eye can look at a star light years away with absolute ease.
And this brings us to a really relatable point. Why does reading up close give you a headache? Well, to use a fantastic analogy directly from our source material, focusing on a near object is like a teacher dealing with a stubborn student. It creates a lot of tension. Here's why. When you look at something far away, the light rays arriving at your eyes are relatively parallel. It's easy work. Your ciliary muscles relax, your lens stays thin, and your eyes are entirely comfortable. But when you look at something right in front of your face, the light rays coming off of it are spreading outwards rapidly. To wrangle those spreading rays and force them to hit the retina perfectly, your ciliary muscles have to tighten aggressively. They make the lens as thick and powerful as possible. Just like a teacher totally stressed out by a difficult student, your eye muscles become tense, overworked, and exhausted. This is exactly why endless scrolling on your phone up close tires your eyes out way faster than staring off into a distant landscape.
Section 3. Vision defect, myopia, nearsightedness.
So, what happens when this amazing hardware fails? Let's start with myopia. Myopia basically means your near vision is perfectly fine, but anything in the distance becomes a total blur. The primary cause here is often that the eye's lens has developed excessive curvature. Basically, it's become too thick and too powerful. Or sometimes, the eyeball itself is simply a bit elongated from birth. The effect of this is that because the lens is too powerful, it bends the incoming light rays far too aggressively. Instead of landing perfectly on the retina at the back of the eye, the light rays converge and form the image too early, right in the fluid before the retina. By the time the light actually reaches the screen at the back, it's scattered and blurry. Now, what's really interesting about this mechanism is how we fix it. How do we correct a biological lens that is just too powerful? We use a concave lens in a pair of glasses. A concave lens naturally spreads light out. By placing it in front of the eye, we force the light to diverge or spread apart slightly before it even enters the eye. This creates the exact amount of extra work that the overpowered eye lens needs, pushing that final focal point perfectly back onto the retina where it belongs.
Section 4. Vision defect, hypermetropia, farsightedness.
Now let's flip it and look at the exact opposite problem, hypermetropia, or farsightedness. Distant objects? Crystal clear, but anything up close? A total blur. The cause here is reversed. The ciliary muscles have weakened, or the lens has just lost its power, preventing it from getting thick enough to handle close-up objects. Alternatively, the eyeball might simply be too short. Because the lens is weak, it struggles to bend those widely spreading light rays coming from a nearby object. It just doesn't converge them fast enough, so the focal point actually ends up forming somewhere completely behind the retina. The screen is getting an unfocused, messy image. To fix this, we need to help the weakened eye. Think of it like using a crutch for a fractured leg. The eye just isn't strong enough to bend the light on its own, so we place a convex lens in front of it. A convex lens converges light. It does a portion of the heavy lifting and bending work before the light even hits the eye. The eye's natural lens essentially says, "Ah, thank you for the help," and takes care of the rest, successfully landing the clear image squarely on the retina.
Section 5. Age and other defects, when the hardware degrades.
Be kind to your elders, folks, because their vision hardware has been working nonstop for decades without a single break. Let's rapidly walk through these 3 distinct conditions that typically arrive with age or physical irregularities. First up, presbyopia. This is essentially old-age hypermetropia. Over decades of constant use, those tiny ciliary muscles we talked about simply lose their flexibility and strength. Quite often, older individuals will actually suffer from both myopia and hypermetropia simultaneously. To correct this, they use bifocal lenses. These are glasses that have a concave lens on the top half for seeing in the distance and a convex lens on the bottom half for reading up close. Next is astigmatism. This happens when the cornea isn't perfectly spherical. Instead, it's irregular or distorted. Because of this uneven shape, the eye literally cannot simultaneously focus on horizontal and vertical lines. If someone with severe astigmatism tries really hard to focus, their eye might visibly quiver. It's fascinating but frustrating. This is usually corrected using specially shaped cylindrical lenses. And finally, cataracts. Now this is a very physical degradation. Over time, a layer of protein can begin to build up directly over the eye's crystalline lens. Slowly but surely, the naturally transparent lens becomes cloudy and completely opaque. If left untreated, it leads to blindness. But fortunately, modern medicine handles this beautifully. Doctors can actually surgically remove the clouded biological lens entirely and replace it with a brand new artificial cellulose lens, completely restoring the person's vision. It's a real medical marvel.
Section 6. Prisms and light. The hidden colors of the world.
Let's move on and see how all this builds into something quite magical. I want you to think about this for a second. Is white light actually white? I mean, when you look up at the sun, it might seem yellow, or if it's a foggy winter morning, the sky might look completely white. We have white light bulbs, white paper, but in the strange and wonderful world of physics, white isn't actually a color at all.
The absolutely crucial point here is that white light is actually a mixture, the whole shebang. It is an optical illusion created when all the visible colors of the spectrum enter our eyes simultaneously. When you pass a beam of natural white light through a triangular glass prism, something incredible happens. Because the light is passing from a rarer medium, the air, into a denser medium, the glass, it slows down and bends. But here's the kicker. White light is made of different wavelengths ranging from 400 to 700 nanometers. Red light has the longest wavelength, so it bends the least. Violet light has the shortest wavelength, so it bends the most. Because they all bend at completely different angles, the prism literally forces the white light to split apart, dispersing it into the beautiful 7-color Vib-Jor spectrum: violet, indigo, blue, green, yellow, orange, and red.
So we've gone from the protective outer shield of the cornea, through the flexible, autofocusing lens, straight to the color-decoding cone cells on our retina, and out into the physics of the Vib-Jor spectrum itself. I'm going to leave you with this provocative thought. If our eyes are this mechanically brilliant, instantly autofocusing on distant stars and decoding the hidden mathematical spectrums of white light all day long, what other invisible wonders is our biology quietly processing right now without us even realizing it? The human body is an absolute marvel of engineering. I really hope this explainer has given you a newfound appreciation for the ultimate biological camera sitting right there in your head. Thank you so much for joining me on this deep dive. Keep learning, keep exploring, and keep asking questions about the amazing world around you. Catch you next time.